1. Engineers often use powers of 10 to simplify their calculations. 10 with the exponent 3, or 10 to the third power, means 10 times 10 times 10. And 10 to the minus 3 means 0.1 times 0.1 times 0.1. However, it is simpler to say that 10 to the third means move the decimal point 3 places right, and 10 to the minus 3 means move the decimal 3 places left. Two. For example, 10 to the sixth means move the decimal 6 places right. So 4.5 times 10 to the sixth equals 4,500,000. 3. 10 to the minus third means move the decimal 3 places left. So 56.5 times 10 to the minus 3 equals 0.0565. 4. We know from the chart that to change from megohms to ohms, we must move the decimal 6 places right. 5.2 megohms equals 5,200,000 ohms. However, by using powers of 10, we can say 5.2 megohms equals 5.2 times 10 to the sixth ohms. 5. Change 800 microvolts to volts. We know that we must move the decimal 6 places left, so we can say 800 microvolts equals 0.0008 volts. Using powers of 10, we can say 800 microvolts equals 800 times 10 to the minus 6 volts. 6. When you find 10 to the minus 6 times 10 to the fourth in a problem, add the exponents algebraically. 10 to the minus 6 times 10 to the fourth equals 10 to the minus 2. 10 to the fifth times 10 to the third equals 10 to the eighth. 10 to the minus 2 times 10 to the minus 3 equals 10 to the minus 5. 10 to the fourth times 10 to the minus 3 equals 10 to the 1, or 10. 7. When a power of 10 is found in the denominator of a fraction, it can be moved to the numerator by changing the sign of the exponent. For example, 4 over 10 to the minus 5 equals 4 times 10 to the fifth. 6 over 3 times 10 to the fourth equals 6 times 10 to the minus 4 over 3, or 2 times 10 to the minus 4, which is equal to 0.0002. 8. The Pythagorean theorem states, in a right triangle, the square of the hypotenuse equals the sum of the squares of the two sides. The area of square 1 plus the area of square 2 equals the area of square 3. 9. In any right triangle, if we know two sides, we can calculate the third. If A equals 4 and B equals 3, find C. C squared equals A squared plus B squared. C squared equals 4 squared plus 3 squared. C squared equals 16 plus 9. C squared equals 25, and C equals 5. 10. Find the unknown side. C squared equals A squared plus B squared. B squared equals C squared minus A squared. Substituting, B squared equals 100 minus 36. B squared equals 64. B equals the square root of 64, or 8. 11. We know that if two batteries are placed in series, the total voltage is the sum of the battery voltages, providing that the two batteries are aiding each other. 12. For example, a 2-volt and a 5-volt battery in series and aiding produce 7 volts. 13. However, if we reverse the 2-volt battery so that it's opposing the 5-volt battery, the total voltage is 3 volts. 14. If we place two AC generators having 100 volts effective voltage in series, what is the total voltage? 15. It may be 200 volts. 16. The total voltage may be 0. What caused the difference? 17. The answer is the difference in starting time, known as phase angle or phase. The generators producing 200 volts were in phase. The generators producing 0 were 180 degrees out of phase. 18. Waveform B is said to lag waveform A 90 degrees because it starts to go positive 90 degrees later than A. The phase angle is 90 degrees, or we can say A and B are 90 degrees out of phase. 19. Waveforms A and B are in phase because they pass through 0 together and hit their positive and negative peaks at the same time. 20. Waveforms A and B are 180 degrees out of phase because B starts to go positive 180 degrees after A started to go positive. Although they go through 0 at the same time, A is going positive while B is going negative. 21. How then can we calculate the total voltage when two AC generators are placed in series? One way is to add the voltages at any instant to find the total voltage. In the instant shown, one generator is developing 50 volts, the other 60 volts, and the total is 110 volts at this instant. 22. If two sine waves having different amplitudes and phase, but identically the same frequency are added, the result will be a sine wave of the same frequency. 23. It is more convenient to add sine waves by means of vectors. This is a vector. 24. A vector stands for a sine wave. 25. The length of the vector represents the peak voltage of the sine wave. 26. The angle between the vector and the base line represents the angle of the sine wave being considered. 27. X and Y are the same. The distance from the head of the vector to the base line represents the voltage of the sine wave at that angle. 28. If we let the vector rotate, the distance from the head of the vector to the base line will describe a sine wave. We always assume that a vector rotates counterclockwise. The picture shows how the voltage represented by the distance from the head of the vector to the base line rises as the vector rotates from 0 to 90 degrees. We are representing a sine wave with 1,000 volts peak voltage, so the vector will be 1,000 units long. (29) As the vector turns from 90 degrees to 180 degrees, the voltage falls to 0. 30. As the vector turns from 180 degrees to 270 degrees, the voltage it represents goes to its negative peak. 31. As the vector turns from 270 to 360 degrees, this negative voltage falls to 0. 32. This mechanical arrangement shows the relationship between a rotating vector and a sine wave. As the wheel rotates, the pen is moved up and down, drawing a sine wave on the paper which moves beneath. Each position of the vector represents a definite voltage on the sine wave. 33. Here we have two sine waves of the same frequency. E2 is twice E1 and lags E1 45 degrees. 34. We can show this information more clearly with vectors. The vector diagram shows that voltage 2 has a peak value twice as great as voltage 1 and lags by 45 degrees. 35. A vector diagram is a high-speed photograph of a rotating vector. These two diagrams show exactly the same information the preceding diagram showed, that E2 is twice E1 and lags 45 degrees. The only difference is that the diagrams represent different times. (36) Here we have two generators of the same frequency, series connected, in phase. By adding the two sine waves at every instant, we obtain a new sine wave, E total. 37. We can add two sine waves more easily using vectors. When vectors are in phase, the resultant is simply a new rotating vector, which is the sum of the other two vectors. It will be in phase with them. 38. A 60-cycle generator having a 1,000-volt peak and another 60-cycle generator having a 2,000-volt peak are connected in series. E1 lags E2 by 90 degrees. The sine wave diagram shows the two voltages. 39. Adding the two sine waves at every instant produces the dotted line E total. 40. The vectors representing the generators look like this. 41. To add the two vectors, draw the dotted lines parallel to the 1,000-volt and 2,000-volt vectors, thus forming a parallelogram. 42. The resultant or total voltage vector will be the diagonal of the parallelogram formed. If we have laid the vectors off to scale, we can measure the resultant and find it to be 2,236 volts. 43. Since the vectors are 90 degrees apart, the parallelogram will be a rectangle. The shaded triangle will be a right triangle, and instead of measuring, we can use the Pythagorean theorem to find E total. 44. E total equals the square root of 1,000 squared plus 2,000 squared. E total equals the square root of 1 million plus 4 million. E total equals the square root of 5 million. E total is 2,236 volts. 45. Whenever two AC voltages in series are exactly 90 degrees apart, we can use the Pythagorean theorem to calculate the resultant vector without actually drawing it. E total equals the square root of E1 squared plus E2 squared. 46. When S1 is closed, the current rises immediately to 1 ampere. When S1 is opened, the current drops immediately to 0. The current through a resistor at any time follows Ohm's law. I equals E over R. (47) When a sine wave of voltage is applied to a resistor, a sine wave of current results which is in phase with the voltage. 48. When S1 is closed, the current is high, being limited only by the resistance. But as the voltage gradually builds up across the condenser, the current drops to 0. Notice that when the voltage across the condenser is 0, current is maximum. And when the voltage across the condenser is maximum, the current is 0. (49) When a sine wave of voltage is applied to a condenser, a sine wave of current results, which leads the voltage 90 degrees. 50. When S1 is closed, the current rises gradually to its final value, which is limited only by the resistance. At the instant the switch is closed, the starting current is held back by the counter EMF caused by the expanding magnetic field. Since the current at this time is low, the drop across R is low, and most of the voltage appears across the coil. Note that when the voltage across the coil is maximum, the current is 0. And when the voltage across the coil is lowest, the current is maximum. 51. When a sine wave of voltage is applied to an inductance, a sine wave of current results which lags the voltage 90 degrees. 52. The opposition which a condenser offers to the flow of AC through it is called capacitive reactance, X sub C, and is measured in ohms. We can modify Ohm's law to find the current when only capacity is present. I equals E over X sub C. 53. But X sub C increases as capacity and frequency decrease. X sub C can be found from the formula X sub C equals 1 over 2 pi Fc, or 0.159 over Fc, where F is in cycles per second, C is in farads, and X sub C is in ohms. (54) For example, what is the capacitive reactance of a 1 microfarad condenser at 1,000 cycles? X sub C equals 0.159 over 1,000 times 1 times 10 to the minus 6. X sub C equals 0.159 over 10 to the minus 3. X sub C equals 0.159 times 10 to the third, or 159 ohms. (55) If the condenser is placed across a 318 volt, 1,000 cycle generator, how much current will flow? X sub C equals 159 ohms. I equals E over X sub C. I equals 318 over 159. I equals 2 amperes. 56. The opposition offered by a coil to AC is called inductive reactance, X sub L, and is measured in ohms. We can modify Ohm's law for use in this circuit containing inductance alone. I equals E over X sub L. 57. However, the opposition, or X sub L of a coil, increases as the frequency and the inductance increase, according to the formula X sub L equals 2 pi FL. 58. For example, what is the reactance of a 1 Henry coil at 100 cycles? X sub L equals 6.28 times 100 times 1. X sub L equals 628 ohms. 59. How much current will a 100 cycle voltage of 200 volts force through a 1 Henry coil? I equals E over X sub L. I equals 200 over 628. I equals 0.318 amperes. 1. In a right triangle, the longest side is called the hypotenuse. It is opposite to the right angle C. The side opposite angle A is side A. The side opposite angle B is called side B. 2. In both right triangles, the side A is half the hypotenuse and the angle A is 30 degrees. In any right triangle, the angle A will be 30 degrees if the side opposite is half the hypotenuse. 3. A certain ratio between side A and the hypotenuse always results in the same angle A regardless of the size of the triangle. This is the basis of trigonometry. For example, if A divided by the hypotenuse is 0.2588, the angle A is always 15 degrees. If A divided by the hypotenuse is 0.866, the angle A is always 60 degrees. 4. Trigonometry defines this as follows. The sine of an angle equals the side opposite divided by the hypotenuse, or sine of A equals A over the hypotenuse. 5. We can find the sine of any angle from sine tables. A very condensed table is shown here. For example, an angle of 30 degrees has a sine of 0.5. 6. With this table we can find either the angle, the hypotenuse, or the side opposite, providing the other two are known. For example, a triangle has a hypotenuse of 1,000 feet and one side of 707 feet. What is the size of the angle opposite the 707-foot side? The sine of angle A equals the side opposite over the hypotenuse. This equals 707 over 1,000, or 0.707. Looking on the table, we find that the angle 45 degrees has a sine of 0.707. 7. Angle A is 60 degrees. The hypotenuse is 100. Find the side A. The sine of angle A equals the side opposite over the hypotenuse. The sine of 60 degrees equals A over 100. Looking on the table, we find the sine of 60 degrees is 0.866. Therefore, 0.866 equals A over 100, and A equals 86.6. 8. Find the hypotenuse if one angle of a right triangle is 15 degrees and the side opposite is 100. The sine of 15 degrees equals the side opposite over the hypotenuse. 0.258 equals 100 over the hypotenuse. The hypotenuse equals 100 over 0.258, or 387. 9. Another trigonometric function shows the relationship between the side adjacent to an angle, the angle, and the hypotenuse. It is called the cosine. The cosine of angle A equals the side adjacent over the hypotenuse, which equals side B over the hypotenuse. 10. Here is a brief table of cosines. 30 degrees, for example, has a cosine of 0.866. 11. Find angle A. Cosine of angle A equals the side adjacent over the hypotenuse. The cosine of A equals 2.58 over 10. The cosine of angle A equals 0.258. Looking on the cosine table, we find the angle A to be 75 degrees. 12. Find the hypotenuse. The cosine of angle A equals the side adjacent over the hypotenuse. Substituting, the cosine of 30 degrees equals 100 over the hypotenuse. Looking on the table, the cosine of 30 degrees is 0.866. Therefore, 0.866 equals 100 over the hypotenuse. The hypotenuse equals 100 over 0.866, or 115. 13. Find the adjacent side. The cosine of 45 degrees equals the side adjacent over the hypotenuse. 0.707 equals the side adjacent over 1,000. The adjacent side equals 707. 14. A third function shows the relation between an angle, the side opposite the angle, and the side adjacent to the angle. It is called the tangent. The tangent of an angle equals the side opposite divided by the side adjacent. In the picture, the tangent of angle A equals side A over side B. 15. Here is a brief table of tangents. 30 degrees, for example, has a tangent of 0.577. 16. Find angle A. The tangent of angle A equals the side opposite over the side adjacent. The tangent of angle A equals 268 divided by 1,000. Tangent A equals 0.268. Looking on the table, angle A equals 15 degrees. 17. Find the side E. The tangent E equals the side opposite over the side adjacent. Tangent 30 degrees equals E over 1,000. Looking on the table, tangent of 30 degrees is 0.577. Therefore, 0.577 equals E over 1,000, and E equals 577. 18. An AC voltage may be applied to a resistor. The current can be found from the formula I equals E over R, where R is the resistance in ohms. 19. If an AC voltage is applied to a condenser, the current is found from the formula I equals E over X sub C, where X sub C is the capacitive reactance in ohms. 20. If an AC voltage is applied to an inductance, the current is found from the formula I equals E over X sub L, where X sub L is the inductive reactance in ohms. 21. But how can we find the current in a circuit containing combinations of resistance, capacitance, and inductance? For example, what current flows when a 100-volt AC generator is in series with a 100-ohm resistor and a condenser having an X sub C of 100 ohms at the generator frequency? 22. We might suppose that the total opposition would be 200 ohms and that the current would be 0.5 amperes. However, the meter indicates 0.707 amperes. We cannot simply add the resistance and reactance to find the total opposition. 23. This total opposition offered by a combination of resistance and reactance is called impedance Z and is measured in ohms. We can modify Ohm's law for use in AC circuits. I equals E over Z. Z equals E over I. E equals I times Z. First, let us study how to find the impedance of series circuits. 24. In a series circuit, there is only one current common to all parts. It can be represented by a vector. 25. Here we have an AC generator, a resistor, and a condenser in series. The resistance is 3 ohms, and the X sub C of the condenser is 4 ohms at the generator frequency. 1/10 of an ampere of current is flowing. Let us draw a vector diagram showing all the voltages and the current. 26. First, find the voltage across the resistor. E equals IR. E equals 0.1 times 3. E equals 0.3 volts. 27. Now find the voltage across the condenser. E equals IX sub C. E equals 0.1 times 4. E equals 0.4 volts. 28. Since the same current is common to all parts of the circuit, let us draw the current vector as our reference. I equals 0.1 amperes. 29. We know that the voltage across a resistor is in phase with the current, so we can lay down the vector E sub R in line with the current and label it 0.3 volts. 30. We know that the voltage across a condenser lags the current 90 degrees, so we can lay down the vector E sub C 90 degrees behind the current and label it 0.4 volts. We must use the same scale for E sub C and E sub R. 31. In a series circuit, the applied voltage is the vector sum of the voltages across the parts. So if we combine E sub R and E sub C, we will obtain a new vector, E total. First, let us form a parallelogram with dotted lines. 32. The diagonal of the parallelogram will be the vector E total. 33. We can either measure the line to find the value of E total or use the Pythagorean theorem. In the shaded triangle, the sides are 0.3 and 0.4. E total equals the square root of 0.3 squared plus 0.4 squared. E total equals the square root of 0.09 plus 0.16. E total equals the square root of 0.25. E total equals 0.5 volts. 34. To summarize, whenever a resistor and condenser are in series, the voltage across the resistor leads the voltage across the condenser 90 degrees, and the total or applied voltage can be found from the formula E total equals the square root of E sub R squared plus E sub C squared. 35. We know that E sub R equals I times R, and that E sub C equals I times X sub C, and that E total equals I times Z. 36. Let us redraw the vector diagram, substituting IR for the voltage across the resistor, IZ for the total voltage, and IX sub C for the voltage across the condenser. 37. Since I is 0.1 amperes in all equations, we can eliminate it, leaving the vectors labeled R, X sub C, and Z. That is, E sub R, E sub C, and E total have the same ratios as R, X sub C, and Z. 38. We can now see that in the shaded triangle, Z squared equals R squared plus X sub C squared, or Z equals the square root of R squared plus X sub C squared. 39. In our example, R was 3 and X sub C was 4, so Z equals the square root of 3 squared plus 4 squared. Z equals the square root of 9 plus 16. Z equals the square root of 25, or 5 ohms. 40. Because R, Z, and X sub C are not changing quantities, they should not be represented as vectors. It is standard to show their relationship in the series impedance triangle shown here. 41. The angle theta is the angle by which the current leads the applied voltage. The sine of theta equals X sub C over Z. Cosine theta equals R over Z. Tangent theta equals X sub C over R. Using any of these functions, we find that theta is between 53 and 54 degrees in this problem. 42. Let us draw the vector diagram for this resistor and coil in series. 43. Because current is common to all parts of a series circuit, we lay down the current vector first. 44. Then the voltage vector E sub R equals 100 volts is laid down in phase with I. 45. Now draw the vector E sub L equals 100 volts, leading I by 90 degrees. 46. Now form a parallelogram and its diagonal E total. 47. We can draw an impedance triangle and find Z from the formula Z equals the square root of R squared plus X sub L squared. Z equals the square root of 100 squared plus 100 squared. Z equals the square root of 20,000. Z equals 141. This means the total opposition of the circuit to this frequency is 141 ohms. 48. Let us draw the vector diagram for a series circuit with resistance, capacitance, and inductance, where R equals 3 ohms, X sub C equals 10 ohms, and X sub L equals 6 ohms. 49. Since current is common in a series circuit, we lay down the current vector as our reference. Now lay down E sub R equals 3 volts in phase with I. Now lay down E sub C equals 10 volts, 90 degrees behind I. 51. Next lay down E X sub L equals 6 volts, 90 degrees ahead of I. 52. Because E sub C and E sub L are 180 degrees out of phase, the resultant of these two vectors will be a 4-volt vector. Call this E sub X. 53. Now combine E sub X and E sub R. This will give E total. We can see that E total equals 5 and that the current I leads E applied. 54. To draw the impedance triangle for this problem, first lay down R equals 3 ohms. 55. Next lay down X sub C equals 10 ohms extending down from R. 56. Now draw X sub L equals 6 ohms extending up from R. 57. Now find the difference between X sub L and X sub C. Mark this difference, X equals 4 ohms. 58. Draw the hypotenuse of the triangle using R and X as the sides. Mark this line Z. The length of Z will be 5. 59. The general formula for finding the impedance of a series circuit follows. Z equals the square root of R squared plus the parenthesis X sub L minus X sub C squared. We can also use the formula Z equals the square root of R squared plus the parenthesis X sub C minus X sub L squared. Either formula could be used, as the parenthesis X sub L minus X sub C squared will be equal to the parenthesis X sub C minus X sub L squared, no matter whether X sub L or X sub C is the larger. For example, if X sub L is 5 and X sub C is 3, then X sub L minus X sub C squared is 5 minus 3 squared, or 2 squared, or 4. On the other hand, X sub C minus X sub L squared is then 3 minus 5 squared, or minus 2 squared. But minus 2 times minus 2 is plus 4. 60. The phase angle can be found from the formulas. The cosine of theta equals R over Z. The sine of theta equals X over Z. The tangent of theta equals X over R. 61. Let us draw the impedance triangle for this circuit, find the angle of lead or lag, and the total current. 62. First lay off R, X sub C down, and X sub L up. Let us do this to scale. 63. Next find the value of X sub L minus X sub C. This will be 100. Label this value X, and then draw the line Z, which forms the triangle. 64. The impedance Z equals the square root of R squared plus the parenthesis X sub L minus X sub C squared. Z equals the square root of 100 squared plus the parenthesis 400 minus 300 squared. Z equals the square root of 10,000 plus 100 squared. Z equals the square root of 20,000. Z equals 141.4 ohms. Z again is the total opposition of the circuit to this frequency. 65. To find the current, use the formula I equals E over Z. I equals 100 over 141.4. I equals 0.707 amperes. 66. The tangent theta will be x over r. This equals 100 over 100, or 1. Looking on the tangent table, we find that theta equals 45 degrees. Now x sub L is larger than x sub C. Therefore, the current lags the applied voltage in this circuit, and we say that the circuit is an inductive circuit. One. If wire A is moved back and forth across the magnetic field, an AC voltage is induced in the wire. If the circuit is complete, an AC current will flow. 2. Now let us hold the wire still and move the magnets back and forth. An AC voltage is still induced in the wire AB, and if it's a closed circuit, AC current will flow. 3. When a wire cuts across lines of force, a voltage is induced in the wire regardless of whether the wire is moving or the lines of force are moving. 4. When an AC current flows through a coil, a moving magnetic field is produced. The field alternately expands and collapses. 5. Let us call this coil the primary. If another coil called the secondary is placed so that the moving field cuts across its turns, a voltage will be induced into the secondary. Such a combination is called a transformer. 6. At high frequencies, air core transformers are used. 7. But in this discussion, we are concerned only with low-frequency transformers, which use iron cores. The formulas given later apply only to iron core transformers. 8. To keep the primary from drawing excessive current, its inductance must be great enough to hold the primary current to a safe value. This is accomplished by a sufficient number of turns and a sufficiently large iron core. 9. Because X sub L varies with frequency, a transformer designed to operate on 60 cycles may overheat on 25 cycles. 10. A transformer cannot be operated on pure DC because the only opposition to the applied voltage is the resistance of the wire. The only time voltage appears across the secondary is when the magnetic field expands as the DC is applied and when the field collapses as the DC is removed. 11. DC can be used providing it is interrupted, as in the case of a vibrator. Vibrators will be discussed in Lesson 6. 12. Iron cores are used to decrease the reluctance of the core and permit a strong concentrated magnetic field to result. 13. A transformer has a rating called turns per volt. This is found by dividing the number of primary turns by the primary voltage. 14. For example, a transformer having 1,000 primary turns and 100 volts applied has 10 turns per volt. 15. This means that the voltage across one turn is 0.1 volts. 16. If our iron core gives us unity coupling, the voltage induced into one turn of the secondary will be the same as the voltage across one turn of the primary, in this case 0.1 volts. 17. The secondary turns are all in series with each other. 18. The total secondary voltage will be the number of turns times the voltage induced into each turn. 6 turns with 0.1 volts across each gives 0.6 volts total. 19. A simple formula shows the relationship between the primary and secondary variables. NP over NS equals EP over ES, where NP and NS are the number of primary and secondary turns, and EP and ES are the primary and secondary voltages. 20. For example, in a transformer having 100 volts applied, 1,000 primary turns and 40,000 secondary turns, what is E secondary? NP over NS equals EP over ES. ES equals EP NS over NP. ES equals 100 times 40,000 over 1,000. E secondary equals 4,000 volts. NP over NS, or NS over NP, is called the turns ratio of the transformer. It is also the voltage ratio. If the secondary turns exceed the primary turns, the transformer is called a step-up transformer. In this case, we have a 1 to 10 step-up in voltage. 22. If the primary turns exceed the secondary turns, it is called a step-down transformer. In this case, we have a 20 to 1 step-down in voltage. 23. Power equals E times I. The power fed into the primary of a transformer equals the primary voltage times the primary current. 24. The power delivered by a transformer secondary to a load equals the secondary voltage times the secondary current. 25. If a transformer is 100% efficient, the power out will equal the power in, or EP/IP equals ES/IS, or EP over ES equals NP over NS equals IS over IP. 26. This indicates that if the secondary voltage is 18 times the primary voltage, the secondary current will be 1/18 the primary current. 27. If no load is present across the secondary, the primary current is very low. 28. But if a load is placed across the secondary, energy is absorbed from the magnetic field, the counter EMF of the primary drops, and the primary current rises. 29. To find the efficiency of a transformer, divide the power output by the power input. 30. For example, if 100 watts are delivered to a transformer and 80 watts are taken from it, what is the efficiency? Efficiency equals power out over power in. This equals 80 over 100, which equals 0.8 or 80%. 31. What happens to the rest of the power delivered to the transformer? It is lost as heat in the core, where it is called core loss, or as heat in the windings, where it is called copper loss. 32. Copper losses are due to the resistance of the winding and can be found from the formula power equals I squared R. 33. Core losses are of two kinds, eddy current losses and hysteresis losses. 34. Eddy current losses result when the magnetic fields induce currents in the core material. These currents produce heat loss in the core. 35. To reduce eddy current loss, the core is made up of laminations varnished to insulate them from one another. 36. Hysteresis loss is a form of molecular friction. When the current changes direction, the polarity of the magnetizing force reverses, and all the molecules reverse their direction. This constant shifting produces heat. It cannot be completely eliminated, but proper choice of core material will reduce it. 37. Let us follow one cycle of transformer action. The current flowing in the primary is a sine wave. Let us start at the 90-degree position. At this time, the current is very strong but is not changing. Therefore, we have a stationary magnetic field and no voltage is induced in the secondary. 38. The current at 180 degrees is zero, but it is here that it is changing at its greatest rate. It's here that the magnetic field is changing at its greatest rate. It has just collapsed to zero and is about to reverse in polarity and expand again. The voltage induced into the secondary at this time is maximum. 39. At 270 degrees, the current through the primary has hit its negative maximum. At this instant, it is not changing. The magnetic field is stationary and no voltage is induced into the secondary. 40. At 360 degrees or 0 degrees, the current and magnetic fields hit zero but are changing at their maximum rates. The voltage induced into the secondary will be maximum in the opposite direction as before. 41. The voltage in the secondary then lags the magnetic field and the primary current 90 degrees. 42. Here is a typical transformer problem. A transformer has an efficiency of 70%. The primary voltage is 100 volts. The secondary voltage is 500 volts. The secondary current is 4 amperes. Find the primary current. 43. First find the power out. Power out equals E secondary times I secondary. Power out equals 500 times 4. Power out equals 2,000 watts. 44. Now find the power in. Efficiency equals power out over power in. Power in equals power out over efficiency. Power in equals 2,000 over 70%. Power in equals 2,000 over 0.7. Power in equals 2,857 watts. 45. Now find the primary current. Power in equals E primary times I primary. I primary equals 2,857 over 100. I primary equals 28.57 amperes. 46. A transformer has 100 primary turns and 500 secondary turns. 110 volts are applied to the primary. Find the secondary voltage. 47. NP over NS equals EP over ES. 100 over 500 equals 110 over ES. E secondary equals 110 times 5. E secondary equals 550 volts. 48. A transformer has a primary voltage of 500 volts, a secondary voltage of 1,000 volts, and an efficiency of 98% when delivering 10 amperes of secondary current. What is the primary current at this time? 49. First find the power out. Power out equals E secondary times I secondary. Power out equals 1,000 times 10. Power out equals 10,000 watts. 50. Now find the power in. Efficiency equals power out over power in. 0.98 equals 10,000 over power in. Or power in equals 10,000 over 0.98. Power in equals 10,204 watts. 51. Now find the primary current. Power in equals E primary times I primary. 10,204 equals 500 times I primary. I primary equals 10,204 divided by 500. I primary equals 20.4 amperes. (52) A relay is an electrically operated switch. 53. When S1 is closed, the magnetic field closes the relay contacts. When S1 is opened, the spring opens the contacts. 54. With a relay, we can control very high currents from a distance with small wires and small switches. 55. For example, we can start a motor generator set from a remote point using a relay. This system is used to start automobiles where the start switch is a small button located on the dashboard. 56. The relays described are normally held open by the spring, and they close when we energize them. However, we can arrange a relay so that the contacts are normally closed and open when energized. When S1 is closed, the relay is opened. When S1 is opened, the spring closes the relay contacts. 57. Silver and tungsten are often used as contacts because they are good conductors, hard, and resist the corroding effect of the sparking present. 58. Here is a method of reducing the pitting caused by sparking. As the coil is energized, the two contacts first touch each other, and then the top contact slides across the bottom contact as the spring flattens out. The contact surfaces are automatically cleaned at each closing. These are called self-wiping contacts. 59. Here is a double pole relay which closes 2 wires when the coil is energized. The dotted line indicates a mechanical connection. 60. Here is a double pole double throw relay. At the moment, A is connected to A1 and B is connected to B1. When the coil is energized, A is connected to A2 and B is connected to B2. 61. Suppose the 2 wires become shorted at X. The current in the wires between the generator and the short is limited only by the resistance of the wire. The heat generated in the wire may start a fire. Some form of protective device is necessary. 62. A relay can be arranged as an overload relay or circuit breaker. If the current becomes excessive, the magnetic field pulls the relay contacts open and the catch holds them open until the reset button is pushed. 63. A fuse is made of a metal having a low melting point. If the current becomes excessive, the fuse will melt due to the heat produced according to the formula I squared R, where I is the current and R is the fuse resistance. This opens the circuit and prevents further damage. 64. Fuses are rated according to their current carrying capacity and the voltage of the circuit. They are made in many shapes and sizes. We have pictured here 2 common types of fuses. The one at the left is a glass cartridge fuse, very frequently used in radio circuits. It is possible to see whether this fuse is burned out merely by looking at it. In larger fuses, the glass shell is often replaced with fiber. An ohmmeter could be used to check it to see whether it is open. House circuits commonly use the fuse on the right. It is known as a plug type of fuse. A small window at the top is provided for viewing the fuse material. 65. Some types of fuses have a small spring attached to the fuse element. 66. When this type of fuse blows, the spring jerks the 2 ends apart and prevents the establishment of an arc. One. In studying direct current, we found that the sum of the currents flowing to a point equaled the sum of the currents flowing from the point. 5 amperes flow toward point A, and 5 amperes flow from point A. 2. In studying alternating current, the vector sum of the currents flowing to a point equals the vector sum of the currents flowing from the point. 3. In parallel circuits where the current divides, we have such a problem. For example, at points A and B. 4. In a parallel circuit, there is only one voltage common to all parts. It can be represented by a vector. 5. Here we have an AC generator, a resistor, and a condenser in parallel. The resistor is 4 ohms, the condenser 3 ohms at the generator frequency. 12 volts are applied. Let us draw the vectors for all the voltages and the currents. 6. First, find the current through the resistor. I equals E over R. I equals 12 over 4. I equals 3 amperes. 7. Now find the current through the condenser. I equals E over X sub C. I equals 12 over 3. I equals 4 amperes. 8. Because the voltage is common to all parts of the circuit, let us draw the voltage vector as our reference. Lay down E equals 12 volts. 9. We know that the current through a resistor is in phase with the voltage across it. So we can lay down the vector I sub R equals 3 amperes in line with the voltage. 10. We know that the current through a condenser leads the voltage 90 degrees. So we can lay down the vector I sub C equals 4 amperes, 90 degrees ahead of the voltage, and label it I sub C equals 4 amperes. We must use the same scale for all currents. 11. In a parallel circuit, the total or line current is the vector sum of the currents through the branches. So if we combine I sub R and I sub C, we will obtain a new vector, I total. First, let us form a parallelogram with dotted lines. 12. The diagonal of the parallelogram will be the vector I total. 13. We can either measure the line to find I total or use the Pythagorean theorem. In the shaded triangle, the sides are 3 and 4. I total equals the square root of I sub R squared plus I sub C squared. I total equals the square root of 3 squared plus 4 squared. I total equals the square root of 9 plus 16. I total equals the square root of 25. I total equals 5 amperes. 14. We can now find the impedance of the circuit. Z equals E over I. Z equals 12 over 5. Z equals 2.4 ohms. 15. Find the impedance of this circuit where R equals 5 ohms and X sub L equals 5 ohms. 16. Let us assume that some voltage is placed across the circuit. For example, 100 volts. 17. Now find I sub L. I sub L equals E over X sub L. I sub L equals 100 over 5 equals 20 amperes. Now find I sub R. I sub R equals E over R. I sub R equals 100 over 5 equals 20 amperes. 19. Since voltage is common to all parts, lay down E equals 100 volts as the reference vector. 20. Now lay down I sub R equals 20 amperes in phase with E. 21. Next lay down I sub L equals 20 amperes, 90 degrees behind E. 22. Now combine I sub R and I sub L to find I total. 23. Use the Pythagorean theorem to find I total. I total equals the square root of I sub R squared plus I sub L squared. I total equals the square root of 20 squared plus 20 squared. I total equals the square root of 400 plus 400. I total equals the square root of 800. I total equals 28.28 amperes. 24. Now find the impedance. Z equals E over I. Z equals 100 volts assumed over 28.28. Z equals 3.56 ohms. In our problem, we assumed a generator voltage of 100 volts, but the impedance would have been 3.56 ohms if any other voltage had been assumed. 25. To find the angle theta by which the current lags the applied voltage, we can say sine theta equals 20 over 28.28, or cosine theta equals 20 over 28.28, or tangent theta equals 20 over 20, or 1. Looking on the tangent table, we find the angle is 45 degrees. 26. Find the impedance of this parallel circuit where R equals 200 ohms, X sub L equals 400 ohms, and X sub C equals 100 ohms. 27. First assume that we have 100 volts across the circuit. 28. Now find the current through the resistor. I equals E over R. I equals 100 over 200. I equals 0.5 amperes. (29) Now find the current through the coil. I equals E over X sub L. I equals 100 over 400. I equals 0.25 amperes. (30) Now find the current through the condenser. I equals E over X sub C. I equals 100 over 100. I equals 1 ampere. 31. Because voltage is common to all parts of the circuit, lay down E equals 100 volts as the reference vector. 32. Now lay down I sub R equals 0.5 amperes in phase with E. 33. Next lay down I sub L equals 0.25 amperes, 90 degrees behind E. 34. Now lay down I sub C equals 1 ampere, 90 degrees ahead of E. 35. I total is the vector sum of I sub R, I sub C, and I sub L. First subtract I sub L from I sub C because they are 180 degrees out of phase. (36) Now combine I sub C minus I sub L and I sub R in order to get I total. 37. Using the Pythagorean theorem, I total equals the square root of I sub R squared plus the parenthesis I sub L minus I sub C squared. I total equals the square root of 0.5 squared plus 0.75 squared. I total equals the square root of 0.25 plus 0.5625. I total equals the square root of 0.8125. I total equals 0.901 amperes. 38. Now find the impedance. Z equals E over I. Z equals 100 over 0.901. Z equals 100,000 over 901. Z equals 110.98 ohms. 39. The tangent of the angle theta by which the current leads the voltage is 0.75 over 0.5. This equals 1.5. Looking on the tangent table, we find the angle theta is 56 degrees. 40. The power being delivered by a generator to a load at any instant equals the voltage at that instant times the current at that instant. 41. Suppose the generator is developing a sine wave of voltage. 42. If we place it across a resistor, the current will be in phase with the voltage. 43. Let us multiply E times I at every instant and graph the power. The power is positive on both alternations. 44. Now let us place the generator across a coil. The current lags the voltage 90 degrees. 45. Let us multiply E times I at every instant and plot the power. Negative power means the load is returning power to the generator. 46. In any circuit where the current leads or lags 90 degrees, the true power is zero because the power returned to the generator equals the power delivered to the load. A perfect coil or condenser cannot dissipate power. 47. Let us place the generator across a condenser and resistor in series. The current will lead by some angle less than 90 degrees as shown by the vector diagram. 48. Here is the same information in sine wave presentation. 49. Let us multiply E times I at every instant and plot the power. As long as the current leads or lags the applied voltage, some power is returned to the generator. This subtracts from the power being dissipated. 50. The true power dissipated by an AC circuit depends then on the current, voltage, and phase angle. E times I alone is called apparent power because it does not take the phase angle into consideration. 51. For example, suppose in the circuit shown, the voltage applied, 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 the voltage apparent power is E times I, or 100 volts times 10 amperes, or 1,000 watts. How can we find the true power? (52) We can say that the line current is really the result of two other vectors, one in phase with the voltage, the current through the resistor, and the other 90 degrees out of phase with the voltage, the current through the coil and condenser. 53. Only the current through the resistor produces heat according to the formula power equals E times I sub R. 54. How can we find the value of this resistive current? The cosine of the angle equals the resistive current over I total, or the resistive current equals I total cosine theta. 55. True power equals E times I, the resistive current. True power equals E times I cosine theta. In the problem, true power equals 100 times 10 times the cosine of 30 degrees. True power equals 100 times 10 times 0.866, or 866 watts. 56. It can be shown that this same formula will give the true power in any circuit. True power equals E times I times cosine theta, where E and I are effective values, or since only a resistance can dissipate power, true power equals I squared R, where I is the current through the resistor. 57. Cosine theta is called the power factor of a circuit because we obtain true power if we multiply apparent power by the power factor. True power is never greater than apparent power. Power factor is never greater than 1. 58. Here is a vector diagram for a series circuit. Notice that cosine theta equals E sub R over E applied. But E sub R equals IR, and E applied equals IZ. So cosine theta equals IR over IZ, or equals R over Z. 59. Here is the vector diagram for a parallel circuit. Cosine theta equals I sub R over I total. But I sub R equals E over R, and I total equals E over Z. So cosine theta equals I sub R over I total equals E over R over E over Z, which equals E over R times Z over E. So cosine theta equals Z over R. 60. To summarize, apparent power equals E times I. True power equals E times I times cosine theta. True power over apparent power equals cosine theta equals power factor equals R over Z in a series circuit equals Z over R in a parallel circuit, and I squared R gives true power where I is the current through the resistor. E squared over R gives true power where E is the voltage across the resistor. (61) In this series circuit, find the unknown values. Check your work against pictures 62 and 63. (64) In this parallel circuit, find the unknown values. Compare your work with the solutions in picture 65 and 66. Start by finding the currents. In this lesson, we shall show how a power supply can be used in place of a battery to furnish DC. 1. This is the symbol for a diode vacuum tube. 2. It has a glass or metal envelope from which the air has been removed. 3. This is the filament. The purpose of the filament is to emit electrons. 4. This is the plate. The purpose of the plate is to attract the electrons thrown off by the filament. 5. An A battery forces current through the filament and heat is produced. Electrons are boiled off the filament. This is called thermionic emission. In an indirectly heated tube, an element called the cathode throws off the electrons. The cathode is heated by the filament, which is now called a heater. (6) If the plate is made positive by a B battery, it attracts electrons thrown off by the filament. This is called plate current. 7. If the B battery is reversed, so the plate is negative, it repels electrons and no plate current flows. A device which permits electrons to flow in only one direction is called a rectifier. 8. If an AC voltage is applied to the plate, current flows only on the half cycles when the plate is positive. 9. We can graph the applied voltage and the plate current. We have a pulsating DC current, although the applied voltage is AC. 10. We can use alternating current to heat the filament. In a typical tube, the filament requires 5 volts, and a step-down filament transformer is provided to reduce the voltage from 110 volts to 5 volts. The filament does not have time to cool off during the time the AC current passes through zero, and we may consider that it throws off electrons continuously. 11. The voltage required on the plate is often 500 volts or more. We can use a transformer with 2 secondary windings, one to supply the filament voltage and the other to supply the plate voltage. Such a transformer is commonly called a power transformer. 12. Let us place a resistor in series with the circuit. When the top of the secondary is positive, a half cycle of current flows through R, making the top of R positive. 13. On the next half cycle, no current flows and no voltage is present across R. The voltage across R is a pulsating DC voltage. 14. What we want is a steady DC voltage. C1, called a filter condenser, is placed across R. When the top of the secondary is positive, the tube conducts and C1 charges to the peak secondary voltage. 15. On the half cycle, when the top of the secondary is negative, no current flows through the tube. However, C1 discharges through R, partly maintaining the voltage across it during the half cycle when there would have been no voltage across it. 16. Here is a graph of the voltage across the resistor with a small and large condenser. The larger the condenser, the smoother the output voltage. "17. The addition of a choke coil further smooths the output voltage. When the top of the secondary is positive, the magnetic field about the choke expands and keeps the current through R from increasing as fast as it would in the absence of the choke. 18. When the top of the secondary is negative, the current through R decreases. The magnetic field about L1 now partially collapses and helps keep the current through R constant. 19. With the addition of C2, we obtain a nearly pure DC voltage across the resistance. C1, L1, and C2 are called a condenser input filter. 20. The output voltage will be slightly less than the peak voltage. The filter supplies energy to the circuit between pulses. 21. The output voltage of this half-wave rectifier A looks like this. 22. The output voltage of this half-wave rectifier B looks like this. The pulses of B occur 1/2 cycle later than the pulses of A. 23. Let us place rectifiers A and B in parallel. R1 and R2 are in parallel and can be replaced by one resistor. 24. Now the output voltage looks like this. This is called full wave rectification. 25. Here a single transformer with a center tap secondary is used. The negative terminal of the power supply is connected to the chassis or ground. 26. A single tube with two plates can be used. On the half cycle, when the top of the secondary is positive, the top plate conducts and current flows as shown. 27. On the half cycle, when the bottom of the secondary is positive, the bottom plate conducts and current flows as shown. 28. On a half-wave rectifier, the space to be filled by the filter is large. 29. On a full-wave rectifier, the space to be filled is small. Consequently, full-wave rectifiers are easier to filter and are more commonly found. 30. The frequency at which the output pulses occur is called the ripple frequency. In a half-wave rectifier, we have one pulse for each input cycle. 31. In a full-wave rectifier, we have two pulses for each input cycle. 32. This is a bridge rectifier. On the half cycle, when the top of the secondary is positive, current flow is shown by the arrows. Tubes 1 and 2 conduct. Current flows through the load from left to right. Tubes 3 and 4 are idle. 33. On the next half cycle, tubes 3 and 4 conduct, while tubes 1 and 2 are idle. The current still flows through the load from left to right. 34. The output voltage of a bridge rectifier looks like this. A bridge gives full wave rectification without the necessity for a center tap. 35. In this half-wave rectifier, the peak secondary voltage is 1,000 volts. 1,000 volt output pulses are formed. The average voltage of one pulse is 636 volts, while the average between pulses is 0. A DC voltmeter across the output will indicate only 318 volts, the average voltage over one entire cycle. "36. If we place a condenser across the output, it will charge to the peak secondary voltage and remain there. The meter will now indicate 1,000 volts. 37. If we center tap the transformer and use full wave rectification, 500 volt pulses are formed. The average of each pulse is 318 volts. A DC voltmeter will indicate 318 volts. 38. If we place a condenser across the output, it charges to 500 volts and stays there. A meter indicates 500 volts. 39. Here we connect the transformer in a bridge circuit. 1,000 volt pulses are formed. The average of each pulse is 636 volts. The average over one cycle is 636 volts. A DC meter indicates 636 volts. 40. If we place a condenser across the output, it charges to 1,000 volts and stays there. A DC meter now indicates 1,000 volts. 41. To summarize, when a condenser filter is used and the load is light, the output voltage of a half-wave supply is the peak secondary voltage. In this case, 1,000 volts. 42. The output of a full-wave supply is half the plate-to-plate peak voltage. In this case, the output is only 500 volts. 43. In a bridge rectifier, the output is the peak secondary voltage. In this case, 1,000 volts. 44. When the plate of a tube is made negative, it normally does not conduct. However, if the plate is made sufficiently negative, a spark may jump the gap from plate to filament. The tube manufacturer gives a rating called the maximum peak inverse plate voltage, which tells the greatest negative voltage it is safe to apply to a tube. A 5U4 has a peak inverse rating of 1,550 volts. 45. Here is a half-wave rectifier shown as the plate voltage is most negative. On the preceding half cycle, the condenser was charged to 1,000 volts. If ground is taken as zero, the plate is minus 1,000 volts, the filament is positive 1,000 volts, and the peak inverse voltage across the tube is 2,000 volts. In a half-wave rectifier, the peak inverse voltage will be twice the peak secondary voltage, and a tube must be selected which will stand. 46. Here is a full-wave rectifier shown as the top plate is most negative. If ground is zero, the top plate is minus 500 volts. The filament is positive 500 volts, and the peak inverse voltage on the non-conducting plate is 1,000 volts. In a full-wave rectifier, the inverse peak voltage is the same as the peak voltage across the entire secondary. 47. In finding the inverse voltage across the idle tubes of a bridge, it is simpler to assume the conducting tubes are such perfect conductors that they have no drop across them. 48. Here we have replaced the conducting tubes with wires to show there is no voltage drop across them. The inverse voltage across tube 1 is the voltage from A to B, or 1,000 volts, and the same for tube 2. In a bridge, then, the inverse voltage across each of the non-conducting tubes is the full peak secondary voltage. 49. Every source of DC has an internal resistance. As the load is made greater, the current rises, the loss across the internal resistance rises, and the output voltage drops. The no-load voltage of this supply is 1,000 volts. When the full load is conducted, the voltage drops to 800 volts. 51. The percentage voltage regulation of this supply can be found from the formula percentage regulation equals N minus F over F, all times 100. where N is the no-load voltage and F is the full load voltage. 52. Percentage regulation equals 1,000 minus 800 over 800, all times 100. Percentage regulation equals 200 times 100 over 800. Percentage regulation equals 25%. A perfect power supply would have a percentage regulation of 0. 53. Some of the losses that cause the output voltage to drop with an increase in load are in the transformer, tube, and choke. The most important factor is the decrease in average voltage across C1. 54. With no load, C1 cannot discharge, and its voltage looks like graph A. With a light load, C1 discharges some, and its voltage looks like graph B. With a heavy load, C1 discharges considerably, and its voltage looks like graph C. 55. The average voltage across C1 drops rapidly as the load increases. With a full-wave rectifier, C1 cannot discharge as much, and the voltage regulation is better than with a half-wave supply. 56. This is called a choke input filter because L1 is added ahead of C1. 57. The inductance L1 causes the variations in input current at F to be small. The voltage across C1 is more nearly constant than before. The output voltage of this filter is approximately equal to the average output voltage of the rectifier. This type of rectifier has good regulation. 58. A choke has inductance because the expanding and collapsing magnetic field produces a counter EMF. 59. However, when the current reaches a point where the core is saturated, an increase of current beyond this point does not produce any change in the field and no counter EMF. Consequently, a choke appears to have lost inductance when the current is beyond saturation value. 60. If an air gap is added, more current is required for saturation. A choke where the core never saturates under normal operation is called a smoothing choke. 61. A very small air gap would allow the choke to become saturated and lose its inductance with a large increase in current. It would be called a swinging choke. 62. L1 is a swinging choke. If the load is light, the current through L1 is light, and it has its full inductance. The filter acts as a normal choke input filter. 63. If the load draws more current, L1 saturates and loses its inductance. We can consider that L1 is shorted out. The output voltage is characteristic of a condenser input filter under load. This supply has excellent regulation and could be used where a large changing load is present. 64. Mercury vapor, when added to a rectifier, reduces the voltage drop across the tube to about 15 volts. The dot indicates a gas-filled tube. 65. A mercury vapor tube should always be followed by a choke input filter to prevent excessive current surges which might damage the tube as C1 charges. 66. Bleeder resistors improve regulation. When the load is removed, the bleeder still maintains some load on the supply and the voltage does not rise excessively. The bleeder also discharges C1 and C2 when the supply is turned off, protecting the operator. 1. If the magnet is rotated as shown, a sine wave of voltage will be induced in the coil. 2. Here we have plotted the voltage at A with B as reference. 3. Here is a three-phase alternator. As the magnet rotates, 3 sine waves of voltage are produced in the 3 coils. Using the reference points indicated, let us plot the voltages at points A, B, and C as the magnet makes 1 revolution. Let us assume a maximum of 1 volt could be induced in each coil. In the position shown, The voltage at A is 0, B is 0.866 volts, and C is minus 0.866 volts. Call this the 0 degree position. Four. Here the magnet has rotated 30 degrees. A has reached 0.5 volts, B has fallen to 0.5 volts, and C is minus 1 volt. Five. At 60 degrees, A has reached 0.866 volts, B is 0, and C is minus 0.866 volts. Six. At 90 degrees, A has reached 1 volt, B is minus 0.5 volts, and C is minus 0.5 volts. 7. At 120 degrees, A has fallen to 0.866 volts, B is minus 0.866 volts, and C is 0. 8. At 150 degrees, A has fallen to 0.5 volts, B is minus 1 volt, and C is 0.5 volts. 9. At 180 degrees, A is 0, B is minus 0.866, and C is 0.866. 10. At 210 degrees, A is minus 0.5 volts, B is minus 0.5 volts, and C is 1 volt. 11. At 240 degrees, A is minus 0.866 volts, B is 0, and C is 0.866 volts. 12. At 270 degrees, A is minus 1 volt, B is 0.5 volts, and C is 0.5 volts. 13. At 300 degrees, A is minus 0.866 volts, B is 0.866 volts, and C is 0. 14. At 330 degrees, A is minus 0.5 volts, B is 1 volt, and C is minus 0.5 volts. 15. At 360 degrees, A is again 0, B is 0.866, and C is minus 0.866. The voltages are 120 degrees apart. (16) Here are the voltages A, B, and C plotted on the same graph. (17) We might connect the 3 coils to 3 loads as shown here. This takes 6 wires. If the alternator develops a peak voltage of 1 volt across each coil, and if the loads are 1 ohm apiece, a peak current of 1 ampere will flow through each coil and load. (18) Here we have connected the 3-phase alternator to 3 loads using only 3 wires. We say that the alternator is delta connected and that the loads are delta connected. The peak voltage across each load is still 1 volt, and the peak current through each 1 ohm load is still 1 ampere. But the peak current through each connecting wire is now 1.73 amperes, as we will show. (19) The voltage across each resistor is equal to the voltage of the coil which is across that resistor. At 0 degrees, the current through wire A is 0.866 amperes, through wire B 0.866 amperes, and through wire C, the sum of the currents through wires A and B, or 1.73 amperes. If the current flows down through the wire, it will be plotted below the reference line. And if the current flows up through the wire, it will be plotted above the reference line. 20. At 30 degrees, through wire A flows 1.5 amperes. B is 0, C is 1.5 amperes. 21. At 60 degrees, through wire A flows 1.73 amperes, through B, 0.866 amperes, and through C, 0.866 amperes. 22. At 90 degrees, through wire A flows 1.5 amperes, through B 1.5 amperes, and C is 0. 23. At 120 degrees, through wire A flows 0.866 amperes, through B 1.73 amperes, and through C 0.866 amperes. 24. At 150 degrees, the wire A current is 0. Through B is 1.5 amperes, and through C is 1.5 amperes. 25. At 180 degrees, through wire A flows 0.866 amperes, B 0.866 amperes, and C is 1.73 amperes. 26. The next 180 degrees continue in a similar manner. All of the instantaneous currents are shown on this diagram. 27. Thus, in a three-phase, three-wire system with delta-connected balanced loads, the current through any connecting wire is 1.73 times the current through any load. For example, if the current through each load is 10 amperes, the current through each line, A, B, and C, will be 17.3 amperes. 28. Here we have Y or star connected the coils and delta connected the loads. 29. It is more convenient to draw a Y connection in this manner. If the peak voltage of each coil is 1 volt, the peak voltage between any two wires will be 1.73 volts, as we will show. 30. Let us consider the voltage from wire A to C as the alternator makes one revolution. At 0 degrees, the voltage of coil 1 is 0, and coil 3 is 0.866 volts. The sum of these two is minus 0.866 volts from A to C. 31. At 30 degrees, coil 1 is 0.5 volts, and coil 3 is 1 volt. These voltages are aiding, and the voltage from A to C is minus 1.5 volts. 32. At 60 degrees, coil 1 is 0.866 volts, and coil 3 is 0.866 volts. These voltages add, and their total is minus 1.73 volts. 33. At 90 degrees, coil 1 is 1 volt, coil 3 is 0.5 volts. The total is minus 1.5 volts. 34. At 120 degrees, coil 1 is 0.866, coil 3 is 0. The total is minus 0.866 volts. 35. At 150 degrees, coil 1 is 0.5, coil 3 is 0.5. The voltages opposed. The total voltage from A to C is 0. 36. At 180 degrees, coil 1 is 0, coil 3 is 0.866, and the total is plus 0.866 volts. 37. The next 180 degrees continue in a similar manner. At 360 degrees, coil 1 is again 0, coil 3 is 0.866 volts, and the total is minus 0.866 volts. Although the peak voltage across each coil was 1 volt, the peak voltage from A to C was 1.73 volts. 38. In a three-phase, three-wire system, a voltmeter will show the same voltage between any two wires. Thus, 110 volts might be measured from A to B, B to C, or A to C. 39. A single load of lamps requiring 110 volts might be connected across any two wires. 40. However, all three phases of a three-wire, three-phase system should be equally loaded. The load can be delta connected or Y connected. 41. In the delta connected load, each lamp will receive the full voltage of 110 volts. 42. If the load were Y connected, the voltage across each lamp would be 110 divided by 1.73, or 63.5 volts. 43. Three identical transformers may be used to change the voltages in a three-phase circuit. The primaries and secondaries may be either delta or Y connected. Here, both the primaries and secondaries are delta connected. The secondary voltages are simply the primary voltages times the turns ratio. If each transformer is a 1 to 10 transformer and 100 volts are applied between each line, the output voltages will be 1,000 volts between each line. 44. Here both primaries and secondaries are Y or star connected. The output voltages are still the primary voltage times the turns ratio. 45. Here the primaries are delta connected and the secondaries are Y connected. The voltage across each secondary coil will be 1,000 volts, but the secondary line voltages will be 1,000 times 1.73, or 1,730 volts. 46. Here the primaries are Y connected and the secondaries are delta connected. The primary line voltage is 100 volts, but the voltage across each primary coil is 100 divided by 1.73, or 57.7 volts. The voltage across each secondary coil will be 577 volts with a 1 to 10 turns ratio. If we have switches to change from delta to Y in the primaries and secondaries, we can obtain with 100 volts at the primaries, 577 volts, 1,000 volts, or 1,730 volts at the secondaries. '47. Here are three half-wave rectifiers connected to three different phases of a three-phase system. Notice that at any instant, at least one rectifier is producing voltage. 48. If we connect the three half-wave rectifiers in parallel, we have a three-phase half-wave rectifier. Notice that the output voltage never falls to zero. We obtain 3 pulses of output voltage for 1 cycle of input. Therefore, the ripple frequency is 3 times the line frequency. A 60-cycle input gives a ripple frequency of 180 cycles per second. 49. Here is the same circuit redrawn to show the Y secondary. The primary may be connected in delta or Y, but usually is connected in delta to obtain the greatest secondary voltage. 50. Here is a full-wave three-phase rectifier. 51. The output has 6 pulses for 1 cycle of input voltage. If the input frequency is 60 cycles, the ripple frequency is 360 cycles. 52. Let us plot the voltage at A, B, and C with X as a reference. 53. The voltage would be a three-phase voltage. 54. At 0 degrees, C is negative, A is positive. Current flows from C up through V2, down through R, up through V6, and back to A. 55. At 60 degrees, C is negative, B is positive. Current flows from C up through V2, down through R, up through V4, and back to B. 56. At 120 degrees, A is negative, B is positive. Current flows from A up through V3, down through R, up through V4, and back to B. 57. At 180 degrees, A is negative, C is positive. Current flows from A up through V3, down through R, up through V5, and back to C. 58. At 240 degrees, B is negative, C is positive. Current flows from B up through V1, down through R, up through V5, and back to C. 59. At 300 degrees, B is negative, A is positive. Current flows from B up through V1, down through R, up through V6, and back to A. 60. At 360 degrees, C is negative, A is positive. Current flows from C up through V2, down through R, up through V6, and back to A. 61. The unfiltered output of this power supply for each input cycle would appear like this. If the input were 60 cycles, the ripple frequency would be 360 cycles. A relatively small filter is required to produce pure DC. '62. The following pages show pictures of AC motors which will be discussed in detail in the written material.